click on Programs, and the first one we have available is Fault Current. Let's go ahead and select that one, clicking on it. Okay, Fault Current program pops up. The customer is, just do it for a home, so home number 1, and we have a single family scenario here, 25 kVA. We have line to line of 240 volts, line to neutral 120. The first distance is 25 feet from the transformer to the first point that we want to check out. The transformer has a 1.6 ohm impedance. We're using 4/0 aluminum conductors, and these conductors are 3 single conductors in a non-metallic raceway PVC. And on the second point, we're going 25 feet. We're using also 4/0 aluminum conductors in a non-metallic raceway. Okay, that should do it. Let's go ahead and preview, expand it, and let's look and see what we have. Our customer name came up. It's our home number 1, and all of our company information came up here. And it states on the first line, fault current, wiring method 1, 3 aluminum wires in a non-metallic conduit actually, 0 to 600 volts. The second fault current is the same, 3 aluminum conductors in a non-metallic conduit, 0 to 600 volts. And I wanted to point out that these formulas were supplied by Cooper Busman, and we had their permission to use these tables for the calculations, thanks to Cooper Busman. Okay, so continuing, we have a one-phase transformer, size of 25 kVA, line-to-line volts of 240 volts, line to neutral 120. The transformer has 104 amps and impedance of 1.6 ohms, which gives it a multiplier of 62.5. Okay, so then going down the line here, the points we're interested in is we have the total length of run number 1 of 25 feet. We're using 1 run of 4/0 aluminum wire. We have 1 run, no parallels. And from line to line, fault current at point 1, we have 5800 amps. And from line to neutral, fault current available at point 1 is 7159 amps. A little higher there, a lot higher. The second length is from our transformer in the home to the from the transformer to the home, and the second point is from the home to inside the home. We have a length of 25 feet. That run uses 25 feet of aluminum conductors, and the fault current available at point 2 is 5238 amps. So let's go ahead and close this and look at an illustration I've pulled up here. Shows the scenario here. We have a utility transformer, 1.6 ohms impedance, 25,000 watts, 120 240 volt transformer, 25 feet of total distance of wire. Now that's the length of the wire now, and it's 4/0 aluminum wire to this first point. If we were to have a short at this point, 25 feet away, we'd have 7158 amps of fault current available. So this equipment needs to be able to withstand at least this much fault current without blowing up. And most of the service equipment for residential starts at 10,000 amps. So we're well within the limits of the safety at this distance. The second point of fault current is from the main service disconnect, 25 feet of conductors, to the main service panel within the home. And again, we're using 4/0 aluminum wire. And at this point, 25 feet from main service disconnect, we have 5238 amps available fault current right here. Okay, So this concludes the demo on fault current program. Oops, one more thing let's point out. This has a worst case scenario, and what it does is adds in motor loading. We don't use this on the homes, but on industrial settings it'd be very important to know what your motor loading is to add that, because the motors dump their energy back to the line as if they were another transformer.